So we're going to start lesson 4, where we're going to start looking at calculating limits analytically, which means instead of using tables and graphs, which are helpful, especially graphs, they can sometimes be inaccurate, like you can't exactly tell where a y value is, and tables can be really tedious. So we're going to actually introduce these things called limit laws in this lesson, and that will allow us to look at equations and evaluate limits from looking at equations. So that is the overview of what this lesson is going to do. Let you read through the tasks and the objectives. And then actually what I would want you to do to start off is go ahead and hit pause on the video, and I want you to read through the 11 laws. I'm going to briefly talk about them, but I want you to get a chance to really read them. So as you do that, just look at this little disclaimer at the top here. As you read through all of these particular laws or properties, C is a constant, so just be aware of that. And both the limit as x approaches a of f and g exist. They are numbers. So go ahead and press pause for just a second, read through these, see which ones make obvious sense and which ones maybe need a little more explanation. And then I will briefly talk about them and then use them in some examples. Okay, so I think the first two are pretty self-explanatory. If you're taking the limit of a sum or difference of things, then you can just take the limit of each one and then add or subtract them. Same thing with 4 and 5, where it's if you're taking the limit of a product or a limit of a quotient, then you can do the limits first and then multiply or divide. Again, assuming you're not dividing by 0. And then just cycling back to 3 here, if you have a constant times a function, you can just pull that constant out front. So take the limit of the function and then multiply it by the constant. And so I've talked about 5 just a second ago, and then 6 is really just a special application of the product. If you're multiplying a function by itself, then you can take the limit and then just multiply that limit by itself however many times you need to. So there's a quick example, just kind of outlining a few of the laws that we've just talked about. I have some graphs, F and G, and we are going to try to evaluate the various limits that are listed here. So the first one is asking us to do the limit as x approaches -2. And it's a sum as well as a constant multiple. So if we're going to apply these limit laws, we can break up into the sum of the limits as well as pull that constant 5 out in front of that second limit, second term. And so then we'll just go to the graph and evaluate these limits. So as x approaches -2, if I'm looking at the function f, that's this pink function, on both sides of the -2, the y values are approaching this open circle here, which is at 1. And we'll do the same thing for finding the limit as x approaches -2 of g of x. So my x is going to be approaching the same value, but the g function is now this blue line. And it looks like, again, from both sides, those y values are approaching -1. So I would have a grand total of -4. All right, second one is giving me the limit of a quotient. So assuming these limits exist, we should be able to break that up into the limit of the top over the limit of the bottom. I'm going to check the bottom first to make sure that that one's not 0. So the limit as x approaches 2, this time we're at +2. So that is in this area right here. And the bottom is f. So again, that's the pink curve. It's not 0. It's a little bit tough to tell exactly what it is. And maybe a 1.4 or so. And it's okay if you said something close to that, but not exactly that. And then we'll do the limit as x approaches 2 of the g of x. So x is approaching 2, g of x is this blue line, and that one is 0. The y values on both sides are approaching 0, but it's okay to have 0 on the top. 0 divided by 1.4 is just 0. And last but not least, we have a product. So I want to look at the limit as x approaches 1 of this product of things. If I just peek here at x approaching 1, I definitely have a single limit for f, but you can see that that is the point on the g function where the equation changes. And so I have a separate limit from the left and a separate limit from the right. So if I wanted to evaluate this, I'm going to need to break it into two one-sided limits, because that's the only way I can actually have a limit for g that exists, is by looking at the limit as x approaches 1 from the left, and then the limit as x approaches 1 from the right. So I'm going to go ahead and calculate. I'll start with 1 from the left. And so I'm just going to write both of those limits multiplied together. The limit as x approaches 1 from the left. So I'm only looking at from the left side of 1, and f, the y values are approaching 2. And for g, as I'm coming towards 1 from the left, my y values are down here, and they are approaching -2. So from the left, the product of these two limits would be -4. So now I'm going to look at it from the right. So I think we mentioned this already. If I'm coming from the right, the f is still landing at that same value of 2. But now as I come from the right side, I am on the blue, the second half of the blue graph, and that is approaching that open dot there at -1. So the product of those two limits, as I approach 1 from the right, is -2, and you can see that the limit as x approaches 1, the two-sided limit of f of x times g of x, does not exist, and that's because the two one-sided limits are not equal. So it's really important to note that if you are going to try to figure out one-sided limits and see if they're equal to determine whether the two-sided limit exists, you need to use the actual notation. You need to include x approaches 1 from the left, x approaches 1 from the right, the limit. If you don't include any of this part and you just have these things here that are numbers, like 2 times -2 equals -4, 2 times -1 equals -2, and then you say, oh, doesn't exist, you're not making a complete statement, because you haven't identified what these calculations actually stand for. And it's a really important aspect as you start to do more sophisticated mathematics, that you outline why these numbers not being equal to each other make a difference. Why does this give you this? And it's because you are calculating the left side limit and the right side limit. And so therefore the both side limit doesn't exist. So I know a lot of you in pre-calculus kind of felt like as long as you got to the answer, that's all that matters. But certainly by the time we are here, we need to be sure that we are including all of the reasoning behind and all of the notation behind what we're actually doing. It's a critical aspect of some of these limit calculations. Okay, And then moving on with our limit laws, I think, again, the rest of these are pretty straightforward. The limit of a constant is just that constant. I mean, if the y's are always equal to 5, then any limit, no matter what x value you're approaching, will be 5. Similarly, if your x is approaching a, then x is approaching a for number 8. So your limit of just plain old x, if x is approaching a, will be a. And then 9 and 10 are just basically combinations of that. If it's x to the n, it'll just be a to the n, or the nth root of x, it'll just be the nth root of a. And same thing for number 11, very similar. Okay, so what we're going to do is we're going to apply these laws in a couple of problems. We are not necessarily going to do limits this way all the time, but these two first examples, we're going to really show each step of applying the laws as we go to find the limit. So I'll start with this first one, and we're going to take the limit as x approaches -3, and you can see here we have a sum. So we will break it into the sum of the 3 terms. And if we were going to identify, that would be the first law, law number 1. Again, it says justify each step here, so I'm just kind of outlining which law I used in that step. For our next step, I think we could go ahead and pull out some constants. For example, we have a negative in front of the x squared and a 6 in front of the x. So we'll pull those two out. I'll just leave the last one alone because we have a limit law that applies to constants, which we'll use next. So I'm pretty sure that was law number 3. Let's double check real fast. Yep, number 3 said that we could pull out the constants. Okay, and then we're going to apply a couple laws at the same time here. So for the first one, we know that if we have the limit as x approaches a of x to the n, that's just a to the n. So we will substitute -3 squared for this limit right here. And that one was, let's see, I've got to find the number. Oh, it's down here. There it is, number 9. Okay. So just going to add that here. Move into the next term. Right before law 9 was law 8 that said the limit as x approaches a of x is just a. So we will substitute for this thing here just the -3, and that was law 8. You can go back and double check that for me. And then the last one, the limit of a constant is just that constant. And that was which one? Number 7. So like I said, you are not going to have to like memorize which laws are which and do this outlining, justifying each step, each law every time. But in the very beginning, as we first start doing it, I'm just going through that to show you. So I have these and I just need to calculate those through. And if I do that, I will get a -36. And so that is my limit as x approaches -3 of this function. Okay. I want you to notice something, and that is if you look at this last calculation here and you look at how it compares to what we started with, -x squared plus 6x plus 6x minus 9, it's the exact same calculation we would have done if we just plugged -3 into the function. And you're going to see in just a minute that that is, in fact, what we're going to be able to do. Again, we're going through a couple of examples to justify how these laws work so that we can see in the end that all we've really done is plug that number in. So we're going to do one more like that for number 2. And in fact, this is a great time for you to give it a try. Do the same thing that I just did. Break it into the different steps using the different laws. Justify each law, figure out where it is, which one are you using, and then come to a final calculation. So go ahead and pause the video while you take a minute to do that. Okay, how did it go? I've gone through my steps here. I just started by breaking it into the limit of the top over the limit of the bottom, which is what Law 5 tells us we can do. And then I have a difference and a sum. So I broke it into the difference of the limits and the sum of the limits, which is the first 2 laws. And then lastly, I applied laws 7, 8, and 9 to do like what we did in the last step in the first problem. So plug the 4 in and square it, plug the 4 in both places here, and then the limit of a constant is just that constant. So those are our first examples. And as you can see, just like in number 1, if I were to take this 4 and plug it directly into x squared minus x over 2 plus x, that's exactly the calculation that we ended up doing. And so you're going to be very happy to see that our first strategy for finding a limit, if you are looking at an equation and you're wondering, how do I find a limit? How do I use these limit laws? The first thing you should always try is direct substitution. Basically, plug in the value that x is approaching directly into the function. And if you actually get a number, it's not usually you will get a number, then that's your limit. So it's a really effective strategy, and it's where we will always start. Okay, so I know that we just went through these examples in extreme detail, but more likely what you're actually going to do if you were trying to find a limit, the instructions will say evaluate. And what does evaluate mean? It means find the value of, and then you're given a limit. So the first thing you're going to try to do is just plug the 3 directly in. And usually if it's a rational function, the place where you're going to get in trouble where it won't work is if the denominator is 0, right? Because you cannot divide by 0, you won't get a number. So a lot of times I'll kind of check that first. I am not going to get 0 in the denominator, so I'm going to keep evaluating here, plugging in everything on the top, plugging the 3 in to everything in the top. So I will have, let's see, 18 plus 12 minus 9 over minus 9 plus 1, which comes out to negative 21 over 8. That is definitely a number. It's not something over 0. And so that will be my limit. So your direct substitution property is always going to be your first try. And if you can plug it in and get a number, then you do that and you're done with that limit, which is really nice.